Our digital world thrives on data, an ever-expanding universe of information that demands faster processing and more efficient storage. From the smallest smart device to the largest supercomputer, the relentless pursuit of speed and capacity defines our technological progress. Yet, beneath this veneer of advancement, a fundamental challenge persists. The very architecture of our computers, born in an earlier era, struggles to keep pace. We are on the precipice of a revolution, driven by a discovery that redefines the very building blocks of electronics. For over a century, the foundation of all electronic circuits has rested upon three pillars: the resistor, the capacitor, and the inductor. These components, each with a distinct relationship between current and voltage, allowed engineers to manipulate electrical signals, giving rise to everything from radios to modern microprocessors. The resistor opposes current, the capacitor stores charge, and the inductor stores energy in a magnetic field. Together, they form the bedrock of our digital civilization, seemingly complete and immutable. However, as early as the 1970s, a nagging theoretical question emerged: what if there was a fourth fundamental circuit element? An element whose properties couldn't be explained by combinations of the existing three. This wasn't just an academic curiosity, it suggested a profound incompleteness in our understanding of electrical systems. The implications were immense, hinting at a new frontier in electronics, waiting to be discovered, one that promised capabilities far beyond what was then imaginable with the established components. In 1971, Leon Chua, an electrical engineer at the University of California, Berkeley, published a seminal paper. He hypothesized the existence of this fourth fundamental passive circuit element, which he named the memristor, a portmanteau of memory and resistor. Chua predicted that this device would relate electric charge and magnetic flux linkage, and crucially, its resistance would depend on the history of the current that had passed through it. It was a theoretical leap, laying the groundwork for a future that would take decades to materialize. So, what exactly is a memristor? At its heart, it's a two-terminal electrical component that regulates the flow of electrical current in a circuit and, unlike a conventional resistor, remembers the last resistance it had. Imagine a resistor that can change its resistance based on how much charge has flowed through it, and then retains that state even when the power is turned off. This intrinsic memory function, directly integrated into its resistive behavior, is what makes the memristor so profoundly different and powerful. The defining characteristic of a memristor is its ability to remember the amount of charge that has passed through it, even after the power is removed. This means its electrical resistance is not constant, it changes based on the history of applied voltage or current. If you push current one way, its resistance might decrease. Push it the other way, and its resistance might increase. And when you stop, it stays at that new resistance state. This makes it inherently non-volatile, a property that unlocks revolutionary possibilities for data storage and processing. For nearly 4 decades, the memristor remained a theoretical concept. Then, in 2008, a team at Hewlett-Packard Labs, led by R. Stanley Williams, announced the successful fabrication of a solid-state memristor. They demonstrated a two-terminal device made of titanium dioxide that exhibited the predicted memristive behavior. This wasn't just another component, it was the realization of Chua's long-sought fourth element, opening the floodgates for practical applications and fundamentally altering the landscape of electronics research. The magic of the memristor lies in its sophisticated material science, typically involving thin films of transition metal oxides, like titanium dioxide or tantalum oxide. These materials possess specific properties that allow them to change their electrical resistance. It's not a simple switch, it's a gradual, analog change influenced by the movement of atoms or ions within the material, creating or destroying conductive pathways. Understanding and controlling these atomic scale dynamics is crucial for memristor performance. At the heart of the memristor's function is a phenomenon called ionic drift, specifically the movement of oxygen vacancies in a metal oxide film. When a voltage is applied, these vacancies, essentially missing oxygen atoms that carry a positive charge, drift through the material. Their movement creates a region with higher or lower conductivity. By controlling the voltage polarity and duration, engineers can precisely modulate the concentration and distribution of these vacancies, thereby tuning the device's resistance and storing information. One of the most appealing aspects of memristors is their structural simplicity. They are two-terminal devices. Unlike transistors, which are typically three-terminal devices requiring a gate, source, and drain to control current, memristors only need two electrodes. This elegant design makes them incredibly compact and easier to integrate into high-density arrays. This intrinsic simplicity is a significant advantage, paving the way for ultra-dense memory and processing units that can fit into ever smaller spaces. To fully appreciate the memristor's potential, it's essential to understand its departure from the transistor. Transistors are switches, fundamental for digital logic, but they require constant power to maintain their state in separate components for memory. Memristors, on the other hand, inherently combine processing and memory functions within a single, two-terminal device. This distinction isn't just about component count, it represents a paradigm shift in how computing can be organized, moving beyond the limitations of transistor-based architectures. The urgency for new computing paradigms stems from the insatiable demand for processing power and data storage. Our current technologies are hitting fundamental physical limits. Moore's law, the decades-long trend of doubling transistor density, is slowing down. We need solutions that are not just incrementally better, but fundamentally different. Memristors offer a path forward, promising to break through these barriers by enabling entirely new architectures that are more efficient, faster, and denser than anything we've conceived before. To grasp the revolutionary potential of memristors, let's look at the current memory landscape. Our computers rely on a hierarchy of memory types, each with its own strengths and weaknesses. At the top, we have fast, volatile DRAM, dynamic random access memory, crucial for active tasks. Below that, slower, non-volatile flash memory serves as long-term storage, found in SSDs and USB drives. This architectural division, though functional, creates bottlenecks and inefficiencies that memristors are poised to resolve. DRAM is the workhorse of our computer's main memory. It's incredibly fast, allowing the CPU to access data almost instantly. This speed is critical for running applications and multitasking. However, DRAM is volatile, meaning it requires constant power to maintain its stored information. Turn off your computer, and all the data in DRAM is lost. This fundamental trade-off, speed for volatility, is a core limitation of modern computing, leading to power consumption and the need for separate, slower, permanent storage. On the other end of the spectrum is flash memory, the technology behind SSDs, USB drives, and smartphone storage. Flash is non-volatile, it retains data even when power is off, making it ideal for permanent storage. However, compared to DRAM, flash memory is significantly slower, especially when writing new data. The process of erasing and rewriting data in flash cells can also degrade the material over time, leading to limited endurance. This speed and endurance gap creates a bottleneck in data-intensive operations. This is where memristors offer a paradigm-shifting solution. Imagine a single memory technology that combines the best of both worlds, the blazing speed of DRAM with the non-volatile persistence of flash. A universal memory that could store data permanently while allowing near-instantaneous access. This unified memory would simplify computer architecture, reduce energy consumption, and eliminate many of the current bottlenecks. Memristors, particularly in the form of resistive RAM, are the leading candidates to realize this dream. Resistive RAM, or ReRAM, is the most promising application of memristor technology for mainstream computing. It leverages the memristor's unique resistive switching property to store data. Each ReRAM cell is essentially a tiny memristor whose resistance state represents a binary 0 or 1, or even multiple bits in a multi-level cell. This technology is being developed to be both ultra-fast and non-volatile, positioning it as a direct successor to both DRAM and flash in future computing systems. It's a game-changer for memory. At its core, ReRAM operates by applying a voltage pulse across a memristor cell. This pulse induces the movement of ions or oxygen vacancies, changing the material's resistance. A set pulse might lower the resistance to represent a 1, while a reset pulse would increase it to represent a 0. To read the data, a small voltage is applied, and the resulting current indicates the cell's resistance state. This entire process occurs at nanosecond speeds, all without requiring power to maintain the stored state. The most immediate and significant advantage of ReRAM is its non-volatility. When the power is removed, ReRAM retains its data, just like flash memory. This means computers could boot instantly, without needing to load the operating system from a slower storage device into DRAM. Imagine a world where your computer is always on, instantly resuming exactly where you left off. This isn't just convenience, it's a fundamental shift in user experience and system design, saving precious seconds and energy every day. Beyond non-volatility, ReRAM promises speeds comparable to or even exceeding DRAM, while offering storage densities similar to, or potentially far greater than, flash. This unique combination allows ReRAM to bridge the performance gap that currently exists between different memory tiers. Future devices could have vast amounts of ReRAM acting as both main memory and storage, eliminating the need for separate, distinct components. This convergence simplifies architecture and enhances overall system performance dramatically. The two-terminal nature and simple vertical stacking possibilities make ReRAM exceptionally dense. Researchers envision 3D ReRAM arrays with multiple layers, packing exponentially more data into the same footprint than planar technologies like DRAM or flash. This scalability is vital for the future, enabling terabytes of memory in compact devices. Imagine a smartphone with the storage capacity of today's largest servers, all accessible at lightning speed. This extreme density fuels the dream of instant-on, always-available computing. The implications are clear. ReRAM has the potential to replace both traditional RAM and SSDs. Instead of distinct components, a single ReRAM module could serve as both ultra-fast working memory and persistent storage. This convergence would eliminate the need for data to constantly move between different memory types, reducing latency, power consumption, and manufacturing complexity. The entire memory hierarchy, as we know it, could be collapsed into a single, highly efficient layer, ushering in a new era for computer architecture. For decades, computing has been shackled by what's known as the von Neumann bottleneck. This refers to the fundamental architectural limitation where the central processing unit, CPU, and memory are physically separated. Data must constantly travel back and forth between them over a relatively narrow bus. As processors get faster, this data transfer becomes the slowest part of the operation, wasting time and energy. It's like having a superfast chef constantly waiting for ingredients to be brought from a distant pantry. The vast majority of energy consumed by modern computers, especially in data centers and AI accelerators, isn't spent on computation itself, but on moving data. Fetching data from memory, bringing it to the CPU, processing it, and then writing it back consumes staggering amounts of power and generates heat. This constant shuttling limits performance and drives up operational costs. Overcoming this data movement problem is one of the most pressing challenges in advancing computing power and efficiency. Enter processing in memory, or PIM. This revolutionary architectural approach aims to break the von Neumann bottleneck by integrating computational capabilities directly into the memory units themselves. Instead of constantly moving data to a separate processor, computations can be performed where the data resides. This dramatically reduces the amount of data transfer, leading to massive gains in speed and energy efficiency, particularly for data-intensive tasks like AI, machine learning, and big data analytics. Memristors are uniquely suited to enable PIM architectures. Their ability to store information and perform basic computational operations within the same physical device makes them ideal candidates. By creating arrays of memristors, engineers can execute matrix multiplications, a fundamental operation in neural networks, directly within the memory array itself, without moving data to an external processor. This analog computing capability is a game-changer, blurring the lines between memory and processing units. The integration of computation into memory cells means that simple logical operations, like AND, OR, and NOT gates, can be performed by simply manipulating the resistance states of memristors in an array. This logic in memory approach radically changes how data is handled. Instead of loading data, performing an operation, and storing the result, the data is transformed in place. This localized processing capability significantly cuts down on communication overhead, accelerating computation, especially for parallel workloads. PIM architectures leveraging memristors are inherently well suited for parallel processing. In a memristor crossbar array, multiple operations can occur simultaneously across different rows and columns. This massive parallelism is exactly what's needed for modern AI algorithms, which often involve large-scale matrix computations. Instead of sequentially processing data, PIM allows for true concurrent execution, leading to orders of magnitude improvements in speed and efficiency for tasks like image recognition, natural language processing, and scientific simulations. By moving computation to where the data resides, memristor-based PIM effectively bypasses the von Neumann bottleneck. The data no longer needs to make round trips to a distant CPU. This direct interaction between memory and processing fundamentally alters the speed and power efficiency equation of computing. For applications like real-time AI, where every millisecond counts, this elimination of the bottleneck isn't just an improvement, it's a transformative leap, unlocking capabilities previously considered unattainable. The implications of PIM extend far beyond AI. Big data analytics, which involves processing enormous datasets to extract insights, is another domain that suffers significantly from the data movement bottleneck. Financial modeling, climate simulations, and genomic sequencing all require immense computational resources. Memristor-based PIM could accelerate these tasks by orders of magnitude, making complex analyses feasible in timescales that are currently impossible, driving new discoveries and informed decision-making across industries. The synergy between memristors and artificial intelligence is particularly profound. The very structure of memristor arrays, their crossbar arrangement and ability to store varying resistance states, maps remarkably well to the synaptic weights in artificial neural networks. This inherent compatibility allows for the direct implementation of neural networks in hardware, moving beyond software simulations to truly analog, energy-efficient AI. It promises a new generation of AI hardware that can learn and process information with unprecedented speed and efficiency. Perhaps the most exciting application of memristors is in brain-inspired, or neuromorphic, computing. The human brain is a marvel of energy-efficient parallel processing, performing complex tasks with just a few tens of watts. This is because computation and memory are deeply intertwined. Memristors, with their ability to store and process information in the same location, offer a hardware analog to biological synapses, making them the ideal building blocks for creating artificial brains that mimic the efficiency and adaptability of biological systems. Consider the staggering efficiency of the human brain. It can recognize a face, understand language, and make complex decisions using dramatically less power than even the most advanced supercomputers. This is largely due to its parallel, distributed processing and the fact that its memory, synapses, and processing, neurons, are not separated. Memristors provide a pathway to replicate this architectural genius in silicon, potentially leading to AI systems that can operate with orders of magnitude less energy, enabling pervasive intelligence. In the brain, synapses are the connections between neurons, and their strength changes based on activity. This is how learning and memory occur. A strong analogy can be drawn between these biological synapses and memristors. The variable resistance of a memristor can directly model the variable strength of a synapse. By arranging memristors in dense crossbar arrays, researchers can create hardware that directly learns and adapts by adjusting these synaptic weights, paving the way for truly intelligent machines. Memristor arrays are ideally suited for implementing artificial neural networks. Data can be fed in as voltage pulses, pass through the array, and the output current reflects the result of the weighted sum, which is the core operation of a neural network. This happens in an analog fashion, avoiding the energy-intensive digital conversions. These arrays can even be designed to learn by adjusting their own resistance values in response to training data, creating self-modifying, autonomous AI hardware that learns on the fly. Most modern computers are digital, meaning they represent information as discrete zeros and ones. While powerful, This requires constant conversion between analog real-world signals and digital data. Memristors excel at analog computing, where computations are performed directly on continuous, variable signals. This can be significantly more energy efficient and faster for certain tasks, particularly pattern recognition and signal processing, by avoiding the overhead of digitization. It's a return to the roots of computing, but with a futuristic twist. The ability of memristors to change their resistance in a continuous, analog manner, and to retain that state, is crucial for hardware-based learning and adaptation. Unlike traditional digital systems that require software updates to learn new patterns, memristor arrays can modify their own physical properties, their synaptic weights, directly in response to new data. This dynamic adaptability is a hallmark of intelligent biological systems, and memristors bring it within reach for artificial intelligence, making AI truly autonomous. Memristors are also ideal for spiking neural networks, or SNNs. These are biologically more realistic neural networks that communicate using discrete spikes or pulses, much like real neurons. Memristors can not only store the synaptic weights but also integrate incoming spikes over time, firing their own spikes when a threshold is reached. This temporal processing capability adds another layer of biomimicry, potentially leading to even more energy-efficient and powerful cognitive computing systems than current deep learning models. Imagine a supercomputer that boots up in milliseconds, not minutes or hours. With ReRAM acting as universal memory, the entire operating system and all applications could reside in non-volatile memory, instantly accessible upon power on. This would revolutionize high-performance computing, eliminating lengthy boot sequences and greatly increasing operational uptime. The implications for critical infrastructure, scientific research, and complex simulations are profound, offering unparalleled responsiveness and efficiency. The bane of all modern computing, the loading screen, could become a relic of the past. From personal computers to enterprise servers, the time spent waiting for software to load or data to transfer could be virtually eliminated. This pervasive instant-on capability, powered by memristor-based ReRAM, would not only enhance user experience but also drastically improve productivity across all sectors. It's a vision of computing that's always ready, always responsive, and always retaining your work, even after a sudden power loss. Data centers, the pulsating heart of our digital world, consume vast amounts of energy and generate immense heat. Memristor-based memory and PIM architectures could transform these facilities. By drastically reducing data movement, they would cut power consumption for memory access and computation. This leads to cooler, denser, and far more energy-efficient data centers, lowering operational costs and environmental impact, while simultaneously boosting performance. It's a greener, faster future for cloud computing and internet infrastructure. The energy savings from memristor technology are not just incremental, they are fundamental. The inherent non-volatility means no standby power is needed to retain data. The PIM approach dramatically reduces the energy spent on data movement, which is currently a dominant factor. At the scale of global data centers and billions of devices, these savings translate into a colossal reduction in electricity demand, offering a critical solution to the escalating energy footprint of our digital civilization. This is efficiency by design, not just optimization. Memristors' compact size and low power consumption also make them ideal for miniaturization and edge AI applications. Imagine tiny sensors, wearable devices, or autonomous drones that can perform complex AI tasks locally, without constantly sending data to the cloud. This intelligence at the edge reduces latency, enhances privacy, and enables truly pervasive smart environments. From smart cities to intelligent prosthetics, memristors empower a new generation of compact, powerful, and always-on intelligent devices. Despite their immense promise, memristors face significant challenges. Fabrication is one of them. Achieving consistent, high-yield manufacturing of memristor devices, especially in 3D stacks, at an industrial scale is complex. The precise control over nanoscale material properties and ionic movement is difficult to maintain across billions of devices. Researchers are continuously refining materials, deposition techniques, and patterning methods to overcome these hurdles and bring memristors to mass production. Another key challenge is variability. The resistive switching behavior of memristors can vary slightly from device to device, and even within the same device over time. This variability impacts reliability and requires sophisticated error correction schemes. Ensuring uniform performance and predictable operation across billions of memristor cells in a large array is crucial for robust computing systems. Overcoming this requires breakthroughs in material science, device engineering, and advanced circuit design techniques. While memristors are non-volatile, their endurance, the number of times they can be switched between resistance states, is another area of intense research. Although significantly better than flash memory, current memristor technologies still have finite write/erase cycles. For universal memory applications, where a cell might be written to millions or billions of times, further improvements in endurance are necessary. Material science and novel device structures are being explored to achieve virtually limitless switching cycles. Despite these hurdles, research and development in memristor technology is booming. Major tech companies and academic institutions worldwide are investing heavily, exploring new materials, improving fabrication techniques, and designing novel architectures. The sheer potential of memristors to solve critical computing challenges, from energy efficiency to AI acceleration, makes this an area of relentless innovation. Each breakthrough brings us closer to a future where memristors are as ubiquitous as transistors are today. As traditional silicon-based computing approaches its physical limits, memristors offer a promising avenue to extend and even redefine the trajectory of Moore's law. They achieve this not by simply shrinking transistors, but by fundamentally changing how computing is done. Their inherent memory and processing capabilities bypass many of the scaling challenges faced by conventional CMOS technology, offering a pathway to continue the exponential growth in computing power and efficiency, ensuring that innovation doesn't stall. We stand at the dawn of a new era in electronics. The memristor, once a theoretical curiosity, is now a tangible reality, poised to become the fourth fundamental circuit element. Its unique properties, non-volatility, speed, density, and integrated processing, are converging to create a computing paradigm that is faster, more efficient, and more intelligent than anything we've known. This isn't just about faster computers, it's about fundamentally rethinking how we build and interact with technology. The convergence of memristor technology with AI, neuromorphic computing, and advanced materials science is shaping a future where intelligence is pervasive, computing is instant, and energy consumption is dramatically reduced. From instant boot laptops to self-learning AI and autonomous vehicles, memristors are the silent enablers of this revolution. They represent not just an incremental improvement, but a foundational shift that will underpin the next wave of technological innovation across every industry. What began as a profound theoretical prediction by Leon Chua in 1971, the memristor has journeyed from hypothesis to laboratory discovery, and now stands on the cusp of widespread commercial application. This journey underscores the power of fundamental research and the relentless pursuit of scientific understanding. The fourth circuit element is no longer a missing piece of the puzzle, it's the key to unlocking the next generation of computing, promising to kill the limitations of RAM and SSDs as we know them. How will memristors change your daily life? Imagine devices that are always on, instantly responsive, and incredibly power efficient. Your phone could boot in a fraction of a second, your laptop never needs to be shut down, and AI assistants become truly intelligent, learning and adapting to your needs with unparalleled speed. The impact will be felt everywhere, from personal gadgets to critical infrastructure, creating a seamless and profoundly more intelligent digital experience. The future of data storage is undeniably memristor-centric. RAM is set to consolidate the disparate roles of RAM and SSD into a single, unified, and highly performant memory tier. This unification will simplify hardware design, reduce manufacturing costs, and unlock unprecedented levels of data access speed and persistence. The era of waiting for data to load or save will rapidly come to an end, paving the way for truly frictionless computing where memory is no longer a bottleneck. Beyond storage, memristors are poised to redefine processing itself. Processing in memory architectures will allow for computations to happen directly within memory, dramatically accelerating data-intensive tasks like AI. This shift will make AI far more powerful, efficient, and accessible, enabling breakthroughs in fields ranging from medicine to climate science. The brain-like parallel processing capability of memristor arrays is the true game-changer, fostering intelligence that can learn and adapt in real time. We are entering a new golden age of electronics, driven by material science innovations like the Memristor. This isn't just about incremental improvements, it's about a fundamental reimagining of how computers work, inspired by the most efficient computing machine known, the human brain. The integration of memory and processing, the non-volatility, and the energy efficiency of memristors are unlocking possibilities that were once confined to science fiction, promising a future of unprecedented computational power and intelligence. The advancements in AI that memristors enable are truly staggering. From vastly more efficient deep learning models to hardware-accelerated neuromorphic systems that learn on-chip, memristors will power AI's next evolutionary leap. This means smarter, faster, and more energy-conscious AI that can operate in a wider range of environments, from tiny embedded systems to massive supercomputers, driving innovation across every conceivable application and transforming our interaction with intelligent machines. For decades, silicon has reigned supreme as the backbone of computing. While silicon will continue to be vital, memristors represent a significant step beyond its traditional limitations, exploring new material properties and architectural possibilities. They open the door to a post-silicon era where different materials and physics are harnessed for computing, pushing the boundaries of what's possible and ensuring a sustained trajectory of technological advancement. The future of computing is diverse, and memristors are at its forefront. The environmental footprint of our digital world is growing. Memristors offer a crucial pathway to mitigate this impact. By enabling vastly more energy-efficient memory and processing, they can reduce the power consumption of data centers, personal devices, and edge computing nodes. This translates directly into lower carbon emissions and a more sustainable technological future. Embracing memristor technology isn't just about performance, it's about building a more responsible and eco-friendly digital world for generations to come. The revolution is not coming, it is already underway. From academic labs to corporate research facilities, the development of memristor technology is accelerating. Prototypes are demonstrating incredible capabilities, and early commercial applications are on the horizon. This isn't hype, it's the culmination of decades of fundamental physics and material science, now ready to redefine the very core of our electronic world. The future of computing will be built on these tiny, intelligent resistors. Memristors are more than just a new component, they demand a complete redefinition of computer architecture. The traditional separation of CPU and memory, a cornerstone for decades, is being challenged. Instead, we envision systems where processing and data storage are seamlessly integrated, working in concert to unlock unprecedented performance and efficiency. This architectural shift will be the defining characteristic of next-generation computing, moving beyond the limitations of sequential processing and into a truly parallel, data-centric era. While challenges remain, the promise of mass-produced, affordable memristor technology is a powerful driver for continued innovation. As manufacturing processes mature and economies of scale take hold, memristors will become accessible across all computing platforms. Imagine the possibilities when every device, from the smallest IoT sensor to the largest cloud server, benefits from instant non-volatile, and processing in-memory capabilities. This widespread adoption will truly kill the limitations of current RAM and SSD technology. Leon Chua's theoretical fourth element, the memristor, has finally come into its own. Its legacy will not just be another component, but a catalyst for an entirely new generation of electronics. It bridges the gap between memory and processing, between digital and analog, and between present limitations and future possibilities. This profound innovation will kill the conventional wisdom of computing, paving the way for systems that are more powerful, more efficient, and more intelligent than anything we could have imagined. In conclusion, the memristor is far more than just another component, it is the realization of a fundamental missing piece in electronics. Its integration promises to usher in a new epoch of computing, where the distinctions between memory and processing blur, where devices boot instantly, and where AI becomes fundamentally more powerful and energy efficient. The journey from a theoretical concept to a revolutionary technology has been long, but the impact of Memristors is now poised to redefine the digital world as we know it, making our computers smarter, faster, and truly alive.